All right, let's jump in on 7.4 then. And in this section, so I freaking love this section, honestly, because so with this whole class so far, we've been talking about integrals, obviously. And we've been talking about like their concrete uses, and we've been getting some really concrete uses of them in the last couple sections. But kind of a thread the whole time has been, integrals find area. And now in the last couple sections, we can rotate that around an axis and give us volume. But we kind of talked about like just by the nature of what an integral is, what it was designed for, that's what it does. It finds area, it finds volume. So I love this section because this is maybe the first section we're going to see where there's maybe, I mean, it'll make sense, but there's a non-intuitive use of integrals. So like integrals end up being used for things that you wouldn't expect them to be useful for. And I think even probably, I mean, the people who invented calculus, Leibniz and I was gonna say Einstein, Newton, yeah, I mean, I think they also they figured that it would be useful for the things we're about to talk about. But I think just from a logical standpoint, just from thinking about what integrals are about, and like we talked about the kind of the age-old problem that they solved, you just wouldn't expect it. And that's fucking beautiful. I mean, that's sorry. But I mean this is college. So like that's freaking amazing. That is so beautiful that you come up with some tool and it solves a problem that you invented it for and you expect it to solve. And then somebody comes along and says, "Hey, actually, we can use this tool for this other thing." And you're just like, "Holy, that's freaking brilliant. Like that's beautiful. Literally, it's beautiful. Like that is just genius, right?" So again, and not that just this just happens with mathematics, actually. You think about engineering, manufacturing, you think about carpentry. This is actually happens for hundreds, thousands of years. Somebody invents a tool, and then somebody comes along and says, "Actually, we could use this another way." And it solves some other problem beautifully. And again, it wasn't designed for that. And it's just freaking beautiful. It's amazing. So that's what I really love about this section. And not so won't see probably maybe a ton of them in this course, but especially in Cal 3, you'll start to see in Cal 3, integrals end up doing some things that you just wouldn't have expected. And it's kind of freaking beautiful. And it's part of, again, what makes science and engineering, the modern iteration of science and engineering work so well is these two tools that we've developed in calculus, derivatives and integrals, actually end up being hella useful tools that solve a crap load of situations that some that you would expect, but some that you just wouldn't expect. And it's like, holy, that's fucking beautiful. That's amazing. So, um, yeah, it really is. It's just awesome. So, okay, so let's dive into it for this section. So for this section, I want to start out. I'll start out with, I guess I'll start out with maybe not a problem, but we'll start out with a function. So I want to start out by really getting you connected to the idea of why this thing works the way it works. However, this is one of those where I know as a teacher and as somebody who just loves this shit, who loves this subject and loves how beautiful and amazing it ends up being, I know that I can spin off and start going really far into this. And so there's a certain amount, I want to do enough to get you connected to the idea of what we're about to talk about and why it works, but I don't want to spin off because then this will be a crazy long video and I will be here till like 2 a.m. So I want to do enough to get you guys to really connect and understand this use we're about to talk about, and especially the equation that comes out of it. Um, and then I just want to get to solving some problems with it. I just want to do the thing. So I I will do that. So let's start. So like I said, this is 7.4. And so what I want to do is let me draw a familiar graph for you, and I'll tell you what the function is that creates that graph. But let's start with a picture. want this to be sizable enough. And that's gonna go up to 5, and that's gonna go up to 5. So I want to start with a parabola. And I want enough curve on it that it doesn't look all straight, but I guess, okay, yeah, we'll sort of size in maybe on this area. In fact, should I make this larger? Yeah, actually, so this is good, but let me actually, not just metaphorically, but actually visually, physically try to size in on this, because we need to see some of this, some of the curve more. So let's try this again. So this time. Let's leave enough room. This time, let's do a bit like this. 1, 2. Let's do then 1, 2, 3, 4. Let's kind of go all the way up there. 5. So let's just extend the y-axis all the way up there. Good, roughly there. And then 1, 2. All right. And so. Something a little more like that. Okay. So this is the function, by the way. So this is the function. Pretty easy to identify. This is x squared plus 1. So the good old parabola moved up 1. And like I said, things we've been worried about is finding area. And then in this last couple sections, finding a volume after you rotate it around, what do you call it, an axis. But let's talk about a different thing, a different aspect of geometry that, so again, the sizing out of just thinking about calculus, area, volume, 2 subjects in geometry that we are hella concerned about. But it's not the only things that we're concerned about in geometry. Another thing that we're very concerned about in geometry is distance, the length along a line, right? And usually in geometry, in a geometry class, we try to make everything straight lines, right? But even in a geometry class, we end up having to deal with circles and the distance around a circle. And we were talking about that actually a little bit in the last lecture. So we have to be able to figure out the distance around non-straight lines, around curves, right? And we were talking about distance in the last lecture too. I was talking about, anytime you need to find the distance between two things, as long as you have a, what do you call it? A number line, a ruler that goes straight between those two things, and you can mark what numbers they sit at, then you subtract. But let's go back to straight lines in geometry. And for straight lines in geometry, we also want to find the distance. But when our 2 points are not straight across from each other, either horizontal or vertical, we do end up using subtraction, but we have to do something else to actually get the distance. So if two points are, I don't know, I guess I'm trying to think of the word that I'm forgetting right now, but are not basically horizontal or vertical, if they're slanted across from each other, catty corner, that's what I'm trying to think of. They're catty cornering from each other. So I want to get you guys to think about, how do you find the distance between 2 points? So I've got, so for a second, let me draw something else on here. So let's forget this for right now. But let's say I have maybe this point here, which is 2, 1, and Let's maybe look at this point here, which is -2, -2. And I want to know the distance between these 2 points. I want to know the distance of the straight line between these 2 points. How do I go about finding that distance? Think about it for a second. Shout at the screen. I won't be able to hear you, but shout at the screen. How do we find the distance there? Good. So hopefully you're shouting Pythagorean theorem, or you're shouting sort of the distance formula, maybe if you memorized it that way. But hopefully you're thinking about Pythagorean theorem. So the way we find the distance between these two things is we figure out the distance here. And then we figure out the distance here. And we use Pythagorean theorem. So let's say, so I'm going to call the hypotenuse here, I'm going to call it D for distance, the distance between those two things. Usually what we would say, this is A, this is B, usually we make it C, but I'll call it D since I'm using the word distance. We would say that D, so if you solve the Pythagorean theorem out, D would be the square root of A squared plus B squared. So A squared plus B squared equals D squared, and I just took the square root of both sides. B squared. Now the question then is, how do you figure out A and B? And so this goes back to, so think about that for a second. How do I find A and B? And this goes back to what I was talking about last time. So when I need to find the distance along the horizontal or vertical, then I can just subtract. So the way I'd find this is I'd take the x value, for instance, for A, I take the x value of this point, and subtract the x value of this point. I would take, so usually the way we'd write this is maybe x2 minus x1, right? So D equals the square root of x2 minus x1 squared. And then how would we find the distance of B? Good. I would just subtract the two y values. That's y2 minus y1. So this would be y2 minus y1. So B is y2 minus y1. So to find the distance, I'm going to take the square root of, and I'm just going to subtract my x values and square it. Subtract my y values and square them and add them together. So if you've seen this formula, hopefully when you see this, you're like, oh yeah, that's that distance formula that they taught me at some point. So at some point in an algebra class, they made you memorize it, or that you had to memorize it. Maybe even you saw this in calculus 1 also. But this is actually where that formula comes from, by the way. So that formula is not a new thing, wasn't a new discovery. It literally is just rewriting the Pythagorean theorem using the coordinates on the points. It's actually just Pythagorean theorem. So Pythagorean theorem is the way we find the straight distance between 2 points, because we can always, if I've got 2 points, I can always draw a straight line between them, and I can always draw a right triangle under that. Another way that you've seen this probably written, especially in a Cal 1 class, is they might have written this as delta x. And they might have written this as delta y. All right. So this is the way that I find distance between 2 points. If they're catty-corner from each other, if they're not vertical, or horizontal. So then the better question though, so that's easy. That's Pythagorean theorem. We've literally known about that for, at this point, literally thousands of years. They knew Pythagorean theorem before Pythagoras kind of codified it. He was just the one that kind of proved that it works abstractly. But the Egyptian civilization, Chinese civilization, Hindi civilization, they knew about this before the Greeks did. And Pythagoras wasn't even trying to pass it off as his own. He didn't say he invented it. He just was the one to prove abstractly why it works. But he was literally just taking this formula that a bunch of literally carpenters, construction, managers had been using for centuries, for probably at least 1,000 years before that, in different civilizations. But he was just taking the formula that they had And they knew functionally that it works because it would make triangles, you're right, it would make triangles work. It would make right triangles for whatever they were constructing. And it, like so it physically worked. He was just the first one to prove it abstract that we know of. So anyway, sorry. So the better question and the harder question, even for architects and people who are doing construction, is, let's say I wanted the length on this curve from, let's say, here to here. So from an x value of 0 to an x value 1, but right along here. The harder question is, how long is that curve? Because again, whether you call it Pythagorean theorem or not, what we've known for thousands of years is how to do this to find straight distance. But then how do you find curve distance? And the funky thing is basically there wasn't a formula for that, and there hasn't been a formula. So there's a formula for a circle. And again, even before the Greeks, they had a rough idea. They didn't have the exact formula, but they had a rough idea actually of the distance around a circle, the circumference of a circle. So you can get the distance around a circle, right? And they had really good approximations of it. Again, the Greeks were the first one to basically probably come up with the formula, but also really prove that the formula worked. So let's say you're building a well or something like that. I can figure out how much wood I need to go all the way around that well, right? I can figure out how much stone, linear distance of stone I would need to kind of place it around that well. But this is not a circle. This is some other weird curve. And there's not just that weird curve. There's a ton of weird curves. You guys have seen them all through algebra, pre-cal, and cal 1. There's a ton of weird curves that aren't circles and don't have that nice formula or that nice approximation. So how do we find the distance along those curves? So that's the idea we want to talk about and then use in this section and that's what they were trying to get at. Again, one of the things they were trying to get at with calculus, with inventing calculus, was, but I mean, this curve has a pattern, has an order, right? So there should be a way to find the distance along that curve. And we couldn't do it for a long time. And then calculus comes along and ends up figuring out a way to do it. So let's talk about the way that we figured out to do it. By the way, so they call this arc length. So an arc, they end up using, arc honestly was originally used for a portion of the circumference of a circle, the edge of a circle, but they end up using arc more as a general term for basically any portion of a curve. So I'll call it the arc length, but yeah, so the question is, how do we find that distance? So I want to keep this over here, but let me erase this so that I don't clutter up the screen here. So let's erase this for now. So first guess. So I'm going to make a first guess that I know is wrong, but then let's kind of look at how we can modify that guess to get closer and closer to the real answer. So the first guess is I could just draw a straight line between these 2 points. And I can calculate the distance of that line, that dotted line. And we know obviously that's not the distance. In fact, we can see and we can prove geometrically that distance along this curve has to be greater than the distance I see there for that straight line between those 2 points. But this is at least, so it's an under approximation, but it's an approximation, right? So I could do that, but obviously that's not the right answer. That's not the distance along that curve. So instead of that, what if I kind of split up? So again, what I'm doing is I'm gonna sort of block or make visually, I get you to focus on this area. So I'm sort of looking at the curve in this area. So what I'm going to do is I'm going to break up this little length of the curve into small pieces. So maybe I'm going to focus on this point where I'm starting on the left, but I'm going to focus on this little point here along the curve. And what I can do then is I can draw a straight line between those 2 points. Now that straight line between those 2 points, again, if you focused in on this curve, if you zoomed in, zoom is the correct word I'm actually thinking of. If you zoom in on that curve, this little line that I just drew is gonna be less than that curve length. But it's gonna be a lot closer to that small portion of the curve, the length of that small portion of the curve. So what I can do is I can draw a little line there, and I can draw a little line to the next point, and I can draw a little line to the next point, and this is visually this is going to be hard, but hopefully you guys kind of get the idea. I can draw a bunch of small straight lines along this curve from one point to kind of the next one that's just delta x. It's just a little past, the x value is just a little past the previous one. And all of these little straight lines, if I add them up, again, I'm going to get something under the value of the curve, but I'm going to get something really close to the value of the curve. So hopefully the visual works, because I think that, just hopefully the visual works in your mind, because I can't get this as as good as I would like it sort of on the board here. But that's what I'm doing. So I kind of have these, don't want to do that either, but I kind of have these small straight lines that are all along the curve, just a little under the distance of the curve, but pretty close. So what I want to do is I'm going to focus on one of these small straight lines, and I'm going to write out the distance. I'm going to calculate the distance on one of those small straight lines. And so the distance actually is just going to be this formula here, but I'm going to translate it into kind of, what do you call it? I'm going to translate it into the language of calculus. So again, this is our distance formula we're used to for between any 2 points. We can use this formula. So the distance of one of these small straight lines is the square root. And what I'm going to do is I am going to write delta x basically instead of x2 minus x1. So it's not that x2 minus x1 is correct, but because these 2 points are so close to each other, I want to start thinking of the distance between them is just delta x, the distance between the x values. So it'll be delta x squared. And then the distance, whatever these 2 little points are, they have a difference in their y values. And again, that difference in the y values will tell you the vertical distance between the 2 points. So my distance is going to be the square root of delta x squared plus delta y squared. Sorry. So I'm using, like I said down here, I'm basically using delta x and a delta y as just a visual replacement for that x2 minus x1, because that's a lot to write. And because the amounts that we're going to see that we have here when we're picking 2 points that are close to each other are pretty darn small. So delta starts to take on this idea of kind of basically of very small distances. Because again, in calculus, what we end up doing is we take the limit as dx. So that's, by the way, that's where dx and dy come from. I'm sure you saw that in Cal 1, but that's where dx and dy come from. It's just another quicker abbreviation. Instead of saying delta, you're saying d. But yeah, so when you take the limit as delta x and delta y approaches 0, then you get a derivative when you're doing the difference quotient. Then you get an integral when you're adding up those areas. That's, again, we've been using delta x or dx and delta y or dy as our way of saying these small distances that I'm going to eventually take the limit as they approach 0. So delta y squared. So the distance along one of these little lines that I'm using to approximate this curve is the square root of delta x squared plus delta y squared. And what I'm going to do is I'm going to go ahead and then change my notation again. I'm going to write this then as dx and dy. And I'm only going to do this, so the change in notation literally doesn't matter. I haven't told you anything different there, but I'm going to change it because then we're going to do a little algebra with this. We're going to do a little algebraic manipulation. And that algebraic manipulation will kind of lead you to the, kind of the formula we'll talk about. So Let's erase this now. So I'm going to use dx and dy because it's more familiar for us when we're thinking about, when we're writing and thinking about derivatives and integrals. All right, so this tells me the distance of one of these little lines. And so essentially if I want the length along that, that arc, this curve, what I'd have to do is add up all those little lines. And then if I take the limit as delta x and delta y is approaching 0, then, and add them all up, then I would have the actual arc length. And when we take the limit as dx or dy or whatever approaches 0 and we add them all up, we sum them all up, which tool is that? What is that? Which of our tools in calculus is that? That's an integral. So here is the clever thing that still blows my mind. Every time I think about this and teach it, I freaking love it. It still blows my mind out of the water. We're not talking about area or what do you call it? We're not talking about area or volume. What we're saying basically is anytime you need to add up a bunch of small things with the limit of that kind of distance between the things approaching 0, that's an integral. So the thing that is just full tilt crazy here is we're gonna take this formula. This formula will tell us the distance of these little lines, and we're gonna take the limit as dx and dy approaches 0 and add them all up. But to add them all up, we're gonna use an integral, and it'll give us the distance along that curve. Done and done. And this is, like I said, this is a crazy, unexpected use, at least to me, of integrals. But it works. So for instance, so again, if this is the distance of those lines, what you could do here to transform this to get the sum of all, get the length of this curve, the sum of all those little lines is you could actually take the integral of just exactly that. Dx squared plus dy squared. And we would take that integral from 0 to 1. Our x values are moving from 0 to 1. And this would give us the length of that curve. So just like we kind of saw the last 2 sessions, we wrote an area formula and then we turned it into an integral, basically really just adding some notation there. But we turned it into an integral because as when we take the limit as the dx or the dy approaches 0 and add them all up, that's what an integral is. We're doing the same thing here. You write the formula and then you turn it into an integral. However, take a look at this integral I've just created. What's wrong with this integral? Or a better question is, can you do that integral? Forget that there's a function to work with, but can you do that integral the way it's written? Good. Hopefully you're seeing that you're like, okay, well, yeah, but we're missing something. So hopefully, maybe you don't see that and maybe you do, but hopefully you see that you're missing some things. Normally when we do an integral, first of all, we only have a dx or a dy. We don't have anything else. So we'll either have one or the other. And since my limits on this one are my x values 0 to 1, then actually I want to have the dx, but I don't want to have the dy. The dy shouldn't be there. I can't, at least you guys can't, as of this class, do an integral in 2 directions. So you will do that in calculus 3. But also, just in terms of equations, it just wouldn't really apply to this. You wouldn't need to do an integral in 2 directions. So all of our integrals have only had a dx or a dy. So that's one problem here. Another problem then is we also sort of don't have a function to work with. You could argue that there sort of is here. There's a square root, and you don't necessarily always need an x or a y, because you can treat things as coefficients. But in general, the integrals we've been seeing have some function with a dx or a dy pasted on the end, and we don't have that here. So this is true though. This is the formula. You integrate it from 0 to 1 and you've got it, but it's just not in a form, honestly, that we can do anything with. Like theoretically, the integral works. It does the thing, but we can't do it as problem solvers because the algebra, there's no algebra to go from there. So what I'm gonna do is I'm gonna show you guys, we are gonna do some clever algebraic manipulation. Know that there's no like theory behind this that tells somebody to do this algebraic manipulation. This is just playing with the algebra. But you'll see this algebraic manipulation is going to turn what we see here into something that looks like an integral that we've been dealing with. And therefore something we can do. So take a look at the cleverness. So actually integral 0 to 1. So let me write it here. And let's look at the manipulation here. So what would you do to try to turn this into something that we can work with? So we are going to play a game that often gets played. So what I'm going to do is I'm going to divide. Let me. So I'm going to divide all of this by dx squared. But like you've seen before with fractions, I can't just go in there willy-nilly and divide by something, right? I have to balance that work out. I can't change the value of what we're looking at. So if I'm gonna divide by that, what I've also got to do then is multiply by dx squared. And this is all going to be underneath the square root, by the way, because the pieces we're working with are underneath the square root. So let's make that square root bigger. Let's put that all underneath the square root. So I'm going to divide and multiply by dx squared. So first of all, algebraically, do we agree that that doesn't change the value of what we're looking at there? Doesn't change the function, or at least the value. Good. It technically doesn't change it. All I've done is multiply by 1. Dx squared over dx squared is 1. So I actually haven't really changed the value of the function at all. But what this allows me to do is now I can break this piece into 2 fractions, and this dx squared becomes sort of this separate element that I'm going to work with. So I can rewrite this as square root of dx squared over dx squared plus dy squared over dx squared. And then all of this times a healthy dx squared on the end. I can split it up into 2 fractions. Why would I do that? So take a look at what you have there. What can be simplified or rewritten in a different way? So notice that dx squared over dx squared, that's just 1. So first of all, notice that's a huge, again, that's a hella simplification. Suddenly I have a 1 here. Before it was Pythagorean theorem, it was a dx squared plus a dy squared. Now, just by playing a little, footsie with algebra, I get a 1. So first of all, that's nice. So that's just a 1. Second of all, so this you don't get it. You don't get such a nice thing happening here with dy squared over dx squared. They obviously don't cancel, and there's no values there, or even in algebraic form, even like a polynomial that you could try to reduce or something like that. However, let's think back to Cal 1. Dy over dx. What is that an abbreviation for? What does that mean? Good. Dy dx, so it means y prime. It means the derivative of y. And again, I started with, this y that we're using, we're thinking of delta y as a distance, which it is, but y is a function, and a function has a derivative. Most of them. So dy dx, so if you kind of, again, when you look at this, if you recontextualize it in your mind, dy dx is y prime, and we're squaring both of them. So this is really dy dx squared. So this is actually y prime squared. So this is y prime, or the derivative of y, or f prime of x, whatever, however you want to say that, squared. And we're multiplying all that by dx squared. What is the square root of dx squared? What's the square root of anything squared? Whatever that thing is. So the square root of dx squared is dx. So I am going to write a dx now on the end, not underneath the square root, because the square root of dx squared is just dx. It's no longer, you've done the square root. So my formula, which again, like I said, the formula that we're working with, that's Pythagorean theorem. Pythagorean theorem, when you do a little clever algebra, gets transformed into the square root of 1 plus y prime squared. And again, this is the second thing that hopefully just blows your mind. And this is another thing I'll tell you, it should blow your mind, and you should never not let it blow your mind. Again, we've been doing Pythagorean theorem for years in classes. They first in geometry, and then they connected it to algebra, and you saw this connection, and it was really cool. But it was Pythagorean theorem. It was always the same thing. It was the distance between 2 points. You've always seen the same form. What we're saying now, after you've taken not only Cal 2, but now Cal 1. So after Cal 1 and Cal 2, we're saying, wait, hold on. Pythagorean theorem is actually connected to the derivative, to an integral of a square root of a derivative of a function. Craziness, nonsense, but it's true. It works. So this will give us the distance along this curve. And notice the nice thing about this version of kind of what I started here. Again, when y just means the function that we're working with, well, this means that I can find the distance. So if you forget the 0 to 1 here, if you just think about this in general, what I'm saying is I can find the distance along the curve. So like I said, there's a lot of different curves, any curve, as long as I can write an equation for that curve. This y can be whatever you want. So in this problem, in this particular problem, you know, the curve that I've drawn for you, it is x squared plus 1. But by being this general, what we're saying is no matter what y is, this is how you calculate the distance along that curve for whatever your what do you call it, limits are going to be. So this is not only the form, this will be how we calculate the distance along x squared plus 1 from 0 to 1. But this then is actually your general formula. Calculate the distance along any curve. So they call this, I'm sure they call it like the arc length formula or something like that. But this works for any function, any curve. And so, like I said, this is the connection I wanted you guys to make, and sort of the story I wanted to tell is they did it. They figured out a way to calculate the distance along any curve that you can write a function for, that you write an equation for, any of them. As long as, with a couple caveats, you got to be able to take the derivative of it, and then you're gonna have an interesting form after this. You're gonna have the square root of 1 plus whatever that derivative is squared, and you got to be able to do an integral along there. So we're not saying it's not going to work on everything, but it works on a lot of things, a lot of things, a lot of things. Pretty much, again, as long as you can do that derivative and you can do the integral of that whole structure afterwards, then you got it. You can find the exact distance along that curve. So what I'm going to do is let's finish out this integral for this particular function from 0 to 1. But then once we're done with that and we got a calculation, I'm going to rewrite this formula here because this is the key. This formula tells us the distance along any curve. And in this case, with your limits or your direction being basically, you know, yeah, you're using x as your independent variable, basically. So tracking along the x values of that curve. All right, so let's work out the nuts and bolts of this from here. So good. This is going to give us what we're looking for here. So the first thing you got to do then is you got to go back to your y and you got to take the derivative of it. So I won't even pause for that. I'll give you guys a couple seconds on that. What is the derivative of y? What's the derivative of that function? The derivative of that function is 2x. So what we should have here is square root of 1 plus 2x dx. And I want you to again notice that now we have, like I was talking about with the integral before, here we couldn't do the integral because I just didn't have the normal things that we have in an integral. Now we have the normal things. We have a function with a dx, and that function has x in it. So this is easy. This is something we can do. Good. So then I want to do the integral of this function. This is going to require a little bit of substitution, but not even that much. So I'm going to rewrite this as 0 to 1. This is going to be 1 plus 2x to the 1/2 power. And if you make 1 plus 2x your u, then this substitution works out really, really nice. So actually, I think I'll have you guys work through it from there for a second. So I'll pause, you pause, go ahead and finish out this integral and let's see what we get. All right, so let's see where you guys got with this. So if my u is 2x or 1 plus 2x, but same thing really, then my du is going to be 2 dx. So what this ends up being is basically you would have 1/2 of u to the 1/2 power. So I'm going to skip a couple lines here, but you'd have u to the 1/2 power, and then you would integrate it from there. So actually, sorry, let's take those limits. We'll put them the other way, but u to the 1/2 ends up being 2/3 u to the 3/2 when you integrate, and that 2/3 gets multiplied by 2, or sorry, by a 1/2. Yes. So you end up with 1/3, 1 plus 2x, my u, the 3/2 power, and we're gonna evaluate this from 0 to 1. Now notice here, and then we're gonna work the calculation out. Notice here that when you plug in 0, you don't actually get 0. So 1 plus 2 times 0 is 1, and 1 to the 3/2 power is 1. So this first part, the last part is gonna give me 1/3. The first part though, 1 plus 2 times 1 is a 3. So I'm gonna get sort of, I'm gonna get the square root of 3 cubed over 3 minus 1/3, and then we can go ahead and combine that into one piece. So it's going to be the square root of 3 cubed minus 1 all over 3, and that would be the distance along that curve. Square root of 3 cubed. And you could actually do some simplifying there. That would actually be 3 square roots of 3, which would be helpful actually. So I think another way you could write this as square root of 3 minus 1/3. So, but either way, that gives us the distance along the curve there. So we can calculate the distance along the curve. We just need to, again, like I said, the next thing I'm gonna do is I'm just gonna literally write up this formula in general without the limits there, but just to show you that formula, that's our formula. That formula will tell you the arc length along any curve, like I said, that we can write a function for with any limits. And here we did the length along this curve using x as our independent variable. If we could do the same thing, your formula would start out the same way, but we could do the same thing using y as our independent variable and integrating with our limits along the y-axis or with the y values. The only thing that changes basically is you get 1 plus kind of, so your function would be in y, so you'd end up with 1 plus x prime squared dy. So depending on what function we look at, sometimes it's actually easier to write it and integrate it along the y direction essentially. So but that's where we're going to start. So good. So hopefully not only connects, but really kind of makes a little sense for you. Let me write up the general equations and then let's go to town. Let's calculate the arc lengths for a couple of these curves. So arc length So you take the integral from whatever, so from x, I don't even want to write x1 and x2 because I just don't want to get the idea entangled with coordinates. But yeah, from A to B is always going to be the square root of 1 minus. So you can write y prime. I'm going to write f of x prime or f prime. In fact, let's just do, well, yeah. Because I just want to emphasize in this case that x's are independent variable. So, but the derivative of f, whatever f is, dx. This will give you the arc length if you're integrating in the x direction. And if you're integrating in the y direction, then again, that you can kind of probably think through the algebra. You, like I said, you'd start out with the same distance equation, but then you would divide by dy squared instead. And you would get the same thing from there, just reversed. Wait, should be a plus. I don't know why I wrote a minus. So 1 plus. And this will be the square root of 1 plus. Yeah. G of y. So just want to emphasize that y is our independent variable there. Squared. Sorry, and this is squared. This is supposed to be, yeah, I don't need the parentheses there, but that's supposed to be squared. Let's try that again. F prime of x squared. I'll just write the squared there because I think we understand kind of what that means. G prime of y squared dy. If you want to integrate along the y direction, it'll look like this, but it's the same thing either way. So it's just kind of have your equation in terms of y or have your equation in terms of x. Let me actually pause for a second. Let me find the net. Yeah, let me just refine the problems that we're going to. All right, so good. So we have these formulas to work with. I think that, I mean, looking at the problems, I think honestly, I mean, we'll see, but honestly, most of these problems, they give you the information as if you're doing this integral with respect to x. So that kind of works perfect there. But keep both in mind. All right, so, but like I said, let's actually work one out. So let's find the arc length. We're going to find the arc length. So and that's what they'll just say for something like this. Just find the arc length. I guess officially, let me just make this 2 because we technically did 1 already. I just didn't number it, but we'll make this 2. And so again, some of these you'll see just like the last couple homeworks, last 3 homeworks, really. Some of these they'll give you the picture, some of they won't. But again, hopefully at this point, it's like that doesn't matter which way they give it to you. So let's look at one without a picture. This is going to be, so I'm going to look at the function y equals x to the 5th over 10. Sorry. Plus 1 over 6x cubed. And we're going to do this along x from 2 to 5. So you'll start to see in this section, they'll go back to giving you, sometimes they'll give you the limits here using interval notation. So this is just, again, at this point in mathematics, they're going to switch up the notation, honestly, just to keep you flexible. Because again, the true thing I'm trying to say here is from x equals 2 to x equals 5, right? However I say that, whichever language I use to speak that, you know that by now. You should be able to read that, interpret it, translate it, and it should say the same thing to you, whether they use interval notation or inequalities or x, use the actual equation. We mean the same thing. So we want you to be flexible so that you realize that those details don't matter. Just read the thing, whatever language they give it to you, and go run what you know you need to do. So anyway, sorry. All right, so it's this curve, whatever this curve looks like, and we're gonna find the arc length from 2 to 5. All right, so then what we need to do is you basically just need to dress up this formula. You need to plug in the parts of this formula. So we need the the derivative of f, or the derivative of y there. And we're going to square it, and we're going to plug it in there, we're going to plug it in there, and then we're going to square it, and we're going to work it out from there. So my arc length then is going to be the integral from 2 to 5 square root 1 plus, and we need the derivative of that. So that's the first thing I need you to do is go ahead and find the derivative of that. So I'll pause, you pause, go ahead and take a second and figure out the derivative of that. All right, so for the derivative here, this is gonna be what you multiply by 5, move it down 1. So that's gonna be, so we're gonna have 1 plus 1/2, or just write x to the 4th over 2, but 1/2 x to the 4th. And then this one, this is a negative exponent, so we are gonna, again, multiply by -3, but then move down. So this is gonna be minus 1/2 x to the -4. Okay, that's what they did with this. I was wondering how this wasn't, I mean, this wouldn't have been horrible if they didn't make this work out nicely. It just would have been, algebraically, it would have been long. Good. Dx. Good. Squared, sorry. Let's put the square there. Good. So that is my f prime of x, or my y prime. Now we got to go through, we are going to take the integral, but notice that there's a little bit of algebra to do here. You got to take this thing and square it. And when we square it, these aren't multiplied, right? So we actually got to do some distribution there. So that's the next thing I want you to kind of do is I want you to work that distribution. So again, I'll pause, you pause, just take a couple minutes, see if you can work out that distribution there. All right, so let's see what this is. And this is a fun one actually to kind of distribute out. So I'm gonna write it without all the fanfare, without all the kind of pieces, but so what you end up doing is you're gonna have 1/2 x to the 4th times 1/2 x to the 4th. So I'm gonna end up here, well, let's write the rest of it. I have 1 plus, and so it's gonna be what, 1/4 x to the 8th. This is interesting. Huh. They do it like this. Interesting. When you, let's see, so the middle parts here, so it's the middle parts is where it gets interesting. So you're gonna do 1/2 x to the 4th times 1/2, negative 1/2 x to the -4, and you're gonna add 2 of those together. But each of those, so x to the 4th times x to the -4th is x to the 0, or just 1, and 1/2 times 1/2 is, I guess, 1, hold on, oh crap, is that gonna mess it up? Yeah, 1/2 times negative 1/2, it's negative 1/4. But you got 2 of them. So this then should be minus 1/2. Okay, that's how they're gonna make this work. Okay, I see. So the middle there, you should have actually just got minus 1/2. And then on the end, you're multiplying negative 1/2 x to the 4th times itself, so you're gonna get plus 1/4 x to the -8. Small notes, again, you don't have to do this. If it doesn't bother you, then, you know, it doesn't mess you up or bother you, then you don't have to do it. But this is actually one of the reasons, so one of the reasons in this problem that I'm not writing it as fractions is what we're about to do from here, where we have to do some factoring. It's actually helpful to see it as powers instead of fractions. There are other times, other problems that we're gonna work, just other setups, other algebraic simplifications that we're doing, where it's actually more helpful to see it as fractions. So it's just sometimes it's helpful to see it as a fraction, sometimes it's helpful to see it as a power. You get an intuition, not just an intuition, but you sort of get used to when it's nicer to see it, or it's helpful to see it one way, and when it's helpful to see it another way. And it may not matter to you, but hopefully you'll kind of see in this next part that it's helpful actually to see it as powers. Let's do a little more simplifying. Not gonna have enough room. So let's try to make this smaller. 2 to 5, square root 1 minus 1/2 is a positive 1/2. So I'm gonna write this in a particular order to help you see the factoring we're about to do. all of that dx. Now honestly, like you get that and you're just kind of like, okay, what in the world do I do with that? So if you look at this as like kind of you're done with your algebra. So what I'm trying to say is logically, like I think not just logically, but practically, I think anybody would look at this and say, okay, algebra done. I've kind of simplified it as much as possible. Combine like terms, all that kind of good stuff. Now I gotta try to integrate this. And the problem you're gonna run into integrating this, so first of all, notice you have sort of a function within a bigger function. So that's usually that's your one of your tells that substitution is gonna be your method. But substitution requires you to have usually another function outside where that is the derivative of this function you see in here, and we don't have that. So the thing that I would be doing this problem and I would sit here and I'd be like, okay, let me go take the integral of that. And I would realize that I can't use substitution because I don't have that second function outside. And because I don't have the second function outside, I can't do integration by parts either. And this isn't any special form for trig substitution or trig integration. So you kind of look at this and it's kind of like, well, crap, I can't really go anywhere with this with what we know on integrating. So then I would look at this and say, well, so if you end up in that situation, you think the algebra is done, but you realize that you don't have any integration techniques that work. I'm not saying 100% of the time. I don't even know what the percentage, it's a large percentage, but I don't know exactly what it is. But often what that means is that surprisingly, you're not done with the algebra, that there's more simplifying that you can do there, especially for problems they give you in a book like this. Now, in reality, some problem that actually some that means something for an engineering, job that you're going to do, chemist, physicist, etc. So often, probably about half the time, what that means is you actually just can't take the integral of it using mathematical techniques that we know, at least, algebraic techniques that we know. So you end up using numerical analysis and some other ways to essentially get a good decimal approximation of that. Or you plug it into these solvers that use the numerical analysis and these these algorithms that are just made after numerical analysis and some other subjects that you'll study another time, that give you some decent decimal approximations of the answer, right? But so in reality, half the time that means you just can't take the integral. But often, not only in the books, but even in reality, what that means is there's a algebraic simplification that you're not thinking of. And it doesn't mean that it should be easy to think of it or should be easy to see it, but it does mean that it's there. So I'm going to look back at this and say, okay, I'm missing something. There's some sort of simplification that I can do. And what I'm going to take a lead from is I'm actually going to take a lead from, so when we squared this out, you ended up, notice kind of the form that you end up with here. Kind of have 1/4 x to the 8th, 1/4 x to the -8th. We have same thing there, but we ended up with a -1/2. Once I add the 1, it flips it to a +1/2. So this form actually looks very similar to this form. I just have sign change in the middle. So if the sign changes in the middle, what do you think changes here? Good, the sign in the middle should change there. So it ends up that this is actually the result of just doing 1/2 x to the 4th plus 1/2 x to the -4th squared. And again, you can almost see, so I mean, that's a really good, also just a practical, if you're ever stuck in a problem and you realize that there probably is something algebraic that you can do there. I'm not saying that you're not always going to see it in the previous part of the problem, but look, so do again that compare and contrast thing. I would notice that this form looks very similar to this form. So I would bet, not even just as a mathematician, but just as a logical gamer, just as a person trying to game this situation out, I would bet then that whatever created this form is going to be very similar to what creates this form, and therefore what can I can simplify this down or break it to. So in this problem, I'm just lucky that this form was created by this, so I can copy this form. And in this case, then it makes complete sense that if I change this sign, it'll change this sign. And that's what I see there. So that's just a good way to to kind of game through and problem solve some sort of algebra that you're missing in a problem, just in general. Good. And the nice thing about this is then squared and square root cancel each other out. So actually what I'm doing is the integral of 2 to 5 of 1/2 x to the 4th plus 1/2 x to the negative 4th dx. And that is very easily done. So again, realize we started with I was talking about it up here. We started with an integral where we realized I can't do that, at least with the algebra techniques, at least with the techniques from this class that we know. And then, but once you simplify it algebraically, you end up with something that is easily doable with the techniques we know. So again, when you're stuck, go back, especially for problems in a book like this, go back and look for a missing algebra. You know, just go back and look and see if there's a missing algebra simplifications, just something you're not seeing, because it is often that. That's sort of one of their points of in a book like this is they're trying to get you to rehash and problem solve and game with the things you already know, right? So they're not going to give you a ton of problems that are just bats out crazy and use things that you don't even know about, right? They're trying to build on what you already know. So it's again, it's a gaming thing. It's a good hint that there's probably some algebra that you're not seeing. There's some algebraic simplification, because that's what they're trying to get you to do. They're trying to get you to really master that algebra that you did before, but maybe you didn't, you're not like balls out amazing with it, right? You know, so they're trying to get you to be amazing with it. So anyways, good. So this is something that's easily doable. So I pause, you pause, go ahead and work through that. All right, so easy enough from here. So taking the integral, I'm gonna move up to 5 and divide by that. So we're gonna have 1/10 x to the 5th. Give me a second. Did I feel like I'm? Oh yeah, that's why. Okay. And then with the x to the negative 4, I'm gonna move up, divide by that number. So this is gonna be minus 1/6 x to the negative 3. So kind of very similar to where we started. I'm actually curious. Let me just see if, well, again, I think they just made this very specifically work out that way. I think often you're not going to see that. It's going to be similar maybe, but not so exactly similar. So let me just make sure that works. Divide by, so that do it. It's yeah, that's all correct. We're gonna evaluate that from 2 to 5. So this is where, let me kind of do, oh my goodness, 5 to the 5th power, seriously. Okay, well, that's fun. Oof. This is, why did they do from 2 to 5 on this? That's the only part here. It's like, really? Okay. So 5 to the 5th power, 25 times 25 times another 5. So 625, 3,125 divided by 10. It's just horrible numbers. So let me write these out so I can work it in my head. And then 5 to the negative 3 is 1 over 125. 750 minus 1 over 750. And then 2 to the 5th is 32, so plus, well, really minus 32/10. And that's going to end up being plus 1 over 48. And that is really fun to find. Actually, the one thing I'll also kind of not really warn you guys, but just let you know about the homework. This is one of the few homeworks where they are allowing decimals. So the problem will tell you which ones do and which ones don't. But some of these problems are allowing decimals for the answers. I think some of the craziness of the fractions we're seeing here is this is probably one of the problems where they allowed decimals as an answer. But all that notwithstanding, well, honestly, for maybe sake of time on this video, that's correct, just not simplified, but that is correct. So I'll just kind of leave it there for now, but you add all that up, subtract all that up, that is gonna be the length of that curve from 2 to 5. And again, notice we didn't even need to see what the curve was. So again, as long as you have a function for the curve, we've got it. We can find the arc length. And so, like I said, another huge accomplishment of calculus. We can find the slope of a tangent line, we can find the area under the curve, we can find volumes, and we can find arc lengths. All right, so let's do maybe one more, and then there's actually a second half to this section, which again, we'll kind of tag, you'll see it kind of tags on to what we just did in 7.2 and 7.3. But let's do another problem. To find the arc length. This one is going to be do something with some pizzazz. So here it's gonna be y equals the natural log of sine x. Just kind of an interesting function if you try to visualize this. There's some, I mean, on your graphing calculator, but there's some really cool graphers and that give you some really cool visual of this. But we're gonna do this from pi over 4 to 3 pi over 4. Notice my inputs now, I mean, still it's x, right? But these are not integers. These are radians or angle measures because really plugging into sine here. There's an extra, once you get the answer out from sine, you're gonna do the natural log of it, but the answer out from sine is just a decimal anyways. It's a ratio, right? It's just a normal number. So this kind of tracks. You plug an angle in here, you get out some decimal, some nice little ratio, and then you take the natural log of that. Good. But we want to find the arc length from pi over 4 to 3 pi over 4. So we're gonna form this. So from pi over 4 to 3 pi over 4. So here's where, again, like I said, I want to constantly stretch you guys by getting me to do less and you to do a little more, at least you to try to put it together first. And then take a look at what I got and make sure that that it matches and that you understand how, just that you're getting it right and you understand how to get there. So I will pause, you pause, go ahead this time and see if you can put together the whole square root, the whole integral that we got to take. All right, so let's see kind of what you got here. So we want the square roots of 1 plus, and then you need to take the derivative of this. The derivative of this, so you're taking the derivative of a natural log, which means it's going to be 1 over. So there's a little bit of chain rule here. There's not only substitution, but a little bit of chain rule. So the derivative of this is going to be 1 over what's inside the natural log, but you've then got to multiply by the derivative of what's inside the natural log. So what you should have got for this was basically cosine x over sine x, which in fact is tangent x. And depending on what we do with the square root the square root, where this integral goes, we actually may need to write it as cosine x over sine x rather than tangent x. But for now, I'm going to say this looks good. So this is going to be 1 plus tan squared x dx. Good. So that's the setup for this integral. Now we have to do the integral, which, second. I wonder what the tension is here. Give me a second. Let me check to make sure I'm correct, but I'm pretty sure. Well, how does that derivation go? That. 1 plus, oh yeah. Does that work? It does, doesn't it? Yeah, so. Okay, sorry. So then what do we do from here? So notice again that we're in a situation where, I mean, again, I have something inside a square root, and so naturally what I'd like to do is some sort of substitution, chain rule, etc. But I have nothing outside of it. I don't have one function times another. So we're again in a situation where this doesn't naturally break down or work using substitution, integration by parts. So again, what's happening here is there is some sort of simplification we could do here. This time it's not algebraic, since we're dealing with trig ratios. This is something from pre-cal. So there's some identity, some pattern, there's something from pre-cal that allows you to simplify what you're seeing here. And so, and we talked about this a good bit when we were doing the chapter 8 stuff. So what is 1 plus tangent squared x? What does that equal? Good. That equals secant squared x. So this is actually the integral from pi over 4 to 3 pi over 4 of the square roots of secant squared x dx. Erase this for a second so we have the room there. And the square root of squared goes away. I will say, so on these two problems that I've chosen, we just happen to get in these situations. That's sort of where, so one was an algebraic simplification, one was a trigonometric, but in both cases, my overall strategy, the thing I was hoping for, I won't even say looking for, because you're never guaranteed that you're going to get this, but I was hoping to see a squared so that it would cancel with the square root. That's what I was hoping for, and both times I got it. Now again, for these problems in the book, that's going to be a good game to play. That's going to be good gaming. In real life, you're not going to see that as often, right? But still, for the sake of this book and getting you guys to really, again, like I said, their purpose is to get you guys to, you passed algebra and pre-cal. They want you to now master those skills. By the time you're done with Cal 2, like, you should be able to look at anything algebraically and really just play around with it and break it down and simplify it one way or another, depending on the need of the problem. That's really where they're trying to get you. You should master algebra and pre-cal. It shouldn't just be something that you can do or that you passed. So, but this does simplify. So that cancels. And so what we end up getting here is the integral from pi over 4 to 3 pi over 4 of secant x dx. And this is where I'm saying then to do this integral, I want you to keep in mind. So again, we saw integrals like this. So a little integrals like this a little bit in chapter 8, but we also kind of saw some of these in chapter 5 as well. But keep in mind, if you're trying to do this, this doesn't have any nice powers. So in chapter 8, we kind of would usually factor off one of our secants or tangents and try to get it to basically have those extra pieces necessary that were the derivative of some substitution we were going to make. And you don't have that opportunity here. So this is where I was saying, and I mentioned it when we were doing those sections. If you're ever stuck in a situation like that, remember that you always want to try to rewrite things in terms of sine and cosine, basically. This is still going to be, that's interesting. So there's still going to be some issues with this integral, I think. Did I miss something? It's possible I missed something here. What did I miss? The derivative of that is 1 over that and multiplied by cosine over sine. You know what I missed? Well, I don't know if that's going to help us either. Ah, crap, but something I did miss here. So I said cosine over sine was tangent, and that is incorrect. I'm sorry, guys. That's actually going to be cotangent squared, which is going to make this cosecant squared. Gonna make this cosecant. Still feel like something's off. But what else is off about this? So that was wrong. 1 over. Would have actually been nice if that was squared. But all right, I'm gonna pause on my side. You don't have to pause, but I'm gonna pause on my side just to figure out what else I'm missing here. All right, so I didn't do anything wrong. So let's kind of look at this integral from here. So we gotta take the integral of cosecant of x. And kind of a bit like I was talking about well, I was about to start talking about on secant x, but we're running into this issue of usually, again, if you think back to chapter 8, when we did stuff like this had a power where we could factor something off and transform things using Pythagorean identities, and we don't have that advantage here. So I will show you guys through this integral. I will completely admit before we start that what I'm about to show you is some foolishness. So this is like, I don't know who came up with this. Honestly, this is the first one in this entire, this entire semester of teaching this stuff where I actually had to go back and look up the derivation of this. This is one that at least had a feather of an idea. I had an idea of what the answer should be, but it was a question of how to get there. And even I had to look this up. What do you call it? But at the least, in a very obscure, possibly sadistic way, the foolishness I'm about to show you is at least interesting in that, if you, again, thinking about it from a strategy standpoint. So this becomes another really obscure strategy that might occasionally be useful in solving some of these problems, and just sort of, again, it's algebraic. This is both algebraic and what do you call it? Pre-cal manipulation. So it's just, again, kind of obscure, rarely useful, but it is sometimes useful. It's just weird. So anyways, so I completely admit it's foolishness, but let me show you the foolishness so that you've seen it once and you occasionally, rarely might use it. I'm not even saying this class, just some point in the future. And let me make sure I get the foolishness correct. Yeah, it's just odd, but okay. But the foolishness starts from the observation that, yeah, like I can't use any of the trig strategies. I can't even use any substitution or integration by part strategies because I don't have two functions. So sometimes these rare things that come up, in some sense, what you're going to do, kind of like an earlier problem, or at least the derivation on the earlier where we were doing the square roots of dx squared plus dy squared, now showing you how it got to that official formula. So like that, sometimes these weird things that they bring up all center around this idea of like basically multiplying by 1, but in fraction form using some sort of weird setup. So the weird setup this time, I'm gonna multiply by 1, but my 1 is gonna be cosecant x plus cotangent x. Skip the dx over there, that's fine. Yeah, divided by, I didn't really need to look at that, cosecant x plus cotangent x. And that indeed is 1. Question is, why in the world would I ever multiply that by that, right? What I want you to notice, well, so basically, why would I multiply by that? So ultimately our goal is still, I want you to notice what I've done is now I've forced the form of this to be one function times another. And if it's one function times another, then my hope, my gaming here is I want to be able to use either substitution or integration by parts. So this is kind of a weird, again, this is a weird strategy in mathematics where not often, but rarely, we can't go anywhere with something, so we multiply by 1. But we choose that 1, that fraction, to be very clever and appropriately created so that we can force sort of a strategy or a tool that we want to be able to use. And I'm not saying that always works, but it does work sometimes. And it's kind of ridiculous and clever, but it's actually kind of ridiculous that it works, but it does. So that's what we're doing here is I'm saying I'm going to multiply by 1, but my 1 is specially chosen so that I'm forcing an integral strategy that I want to be able to use. So let's see kind of how that does it, how it forces that integral strategy. So again, notice that one thing is now I have one function times another. So again, my leads on this are either substitution or integration by parts. I'm hoping substitution and integration by parts would be horrible. Just the amount of algebra you'd have to do there. So I'm hoping substitution. Also, since I have these two being multiplied, I can go ahead and distribute on the top here because this is really cosecant x over 1. So I'm going to transform this a little. And when I multiply, what I'm going to end up getting is cosecant squared x plus well, it doesn't matter the order really, but cosecant x cotangent x all over cosecant x plus cotangent x. Now, a couple things. So again, what I'm saying here is this is the same as cosecant x, this is where I'm saying this is foolishness. I mean, that is just crazy. And it is. So the thing is, it's technically true. It is cosecant x. Why in the world would I ever go there? I mean, that's just a big mess. Why would I ever take cosecant x and blow it up into some foolishness like that? The reason is I want you to notice that the top here, the pieces in the top here should look a little familiar to you. Cosecant squared is the derivative of what? Good, that's the derivative of cotangent. And notice we have a cotangent on the bottom. What is cosecant x cotangent x? What is that the derivative of? Good, that's the derivative of cosecant. So it just so happens that this 1 that I specially created, specifically for this job, this 1 contains the parts on the bottom end up being, contains the pieces. So this 1, when I multiply through, I end up on the top with the derivatives of the things on the bottom, which means I can use substitution. And again, that is the foolishness of this too. So I literally specifically created this fraction. Somebody had to sit there and think about that for a while, forward thinking that really what we wanted to get to was substitution on a problem that there's no way you could ever use substitution and integration by parts or any trig substitutions at all. I mean, this was dead in the water where it was. And we just brought it back to life with this ridiculous version of 1. But it works. So another small thing that you should always be amazed by and never lose your amazement, that somehow multiplying by a special 1 will literally bring some problems back to life. You couldn't do them and now you can do them, and that is just weird and crazy and cool. All right, but we can do this. So basically then, and let's put a dx here. My substitution, I can do substitution from here. My substitution is going to be the bottom. So this is my u. And if that's my u, so without writing all this, hopefully you guys kind of see it through, or you can pause the video and kind of write it through yourself. That if this is my u, then the top ends up being exactly du with the dx. So we end up with the integral. But we are definitely running out of room on this one. It should have went up higher. But integral from pi over to 4, 3 pi over 4. Basically 1 over u, or du over u. So we'll say du over u. And so this then is going to be the integral. This is natural log of u, which my u is this cosecant x plus cotangent x. So this is going to be the natural log of cosecant x plus cotangent of x, evaluated from pi over 4 to 3 pi over 4. And what I'm gonna do from here is I'm gonna write the answer both to save you some time, because there is several steps of algebra. Once you plug it in, there's still some steps of algebra that involve properties of logarithms, but also honestly to save me some time. So I'm gonna, what I'm gonna have to do is split this lecture into two parts. But what you end up with out of all this, which one ends up top? Well, I will finally cheat, just write down the answer I see in the book, hold on. What you finally end up with out of all this is the natural log. Natural log of square root of 2 plus 1 over the square root of 2 minus 1. So natural log of all of that. And that's actually, that'll be our answer once you plug that stuff in and then start adding, subtracting the fractions together and combining the logarithms together using properties of logarithms. Good. But that would be your answer there. All right. I don't think you'll see anything as complicated in the homework. But like I said, actually, perversely, you will occasionally, very rarely, but you'll occasionally need to do something ridiculous and funky like this. So I do actually want you to see it once. Okay, so yeah, I'm gonna have to split this. So there's a whole nother half to this that, again, like I said, actually plays on what we just learned about with volumes, with rotating curves around an axis, specifically the X and Y axis. So the other half of it, I'll have to leave till tomorrow morning. I'll do that. I'll have to try to do that tomorrow morning before I get onto the tests with my other class. But start with this. Watch this. You'll be able to work more than half the homework. Most of the homework is actually this. But you'll be able to work more than half the homework, and then I'll have the second video up for you to work the other half. All right, so I'll see you guys on the next video.